thought experiments. Most of Einstein's theories are based on thought experiments. For example, the train and the lightning flash thought experiment, from which the relativity of simultaneity is deduced. Although the logic underlying these thought experiments is rigorous, they depart from reality in several significant ways. Trains cannot travel at near the speed of light, and were even slower in Einstein's time. If a train could travel at near the speed of light, it would not be possible for an observer in a relatively stationary frame of reference to observe events in the train. In the relativity of simultaneity thought experiment, what's more, the train would need to be impossibly long. In fact, according to many, it would need to be infinitely long for the effect to in fact be visible. An infinitely long train is impossible for two reasons. It is impossible to construct an infinitely long train. It is just simply not possible to do so. And even if it were possible to construct an infinitely long train, it would be impossible to see flashes of light from either end of the train. As light intensity decreases with the square of the distance from the source, at an infinite distance from the source, and if you're standing in the middle of an infinitely long train, both ends of the train would be an infinite distance from you. At an infinite distance from the source, the light intensity would be 0, as it would be 1 on infinity squared. When Einstein proposed his special theory of relativity in 1905, the experimental and technological capability to verify his predictions did not, in fact, exist. The only experimental evidence came from the Michelson-Morley experiment, which had set out to prove the existence of the ether and ended up proving exactly the opposite. The theory of relativity, however, made a number of testable predictions based on thought experiments, but these predictions were testable, and many of these predictions have since been shown to be accurate. Evidence for a relationship between mass and velocity was first discovered in around 1908. In experiments involving the deflection of electrons in vacuum tubes, it was found that more energy was required to deflect faster electrons. In modern particle accelerators, protons and other particles have been found to need greater and greater energy input to accelerate them as the speed of light is approached. The 1971 atomic clock experiment provided evidence of time dilation with macroscopic or real-world clocks. The results of the experiment confirmed the predictions of the theory of special relativity. Since this time, similar experiments have confirmed the results. Muons. Another source of evidence for the theory of relativity comes from muons, which are short-lived subatomic particles. Muons are formed in the upper atmosphere as a result of bombardment by cosmic rays. They have very short half-lives of around 2.2 microseconds. Given their short half-lives, muons should not be able to reach the surface of the Earth from the upper atmosphere. Half of the muons produced should in fact decay after having travelled less than 500 meters. There are two ways of explaining that the muons are able to survive long enough to strike the surface of the Earth. From the viewpoint of an observer on the Earth, time dilation means that the muons survive to strike the surface. As from the point of view of the observer on the Earth, time in the frame of reference of the muon runs more slowly. From the frame of reference of the muon, length contraction means that they survive to strike the surface of the Earth. From the frame of reference of the muons, length contraction means that they are able to survive long enough to strike the surface of the Earth. Both of these explanations are in fact valid and are not mutually exclusive. In 1919, Arthur Stanley Eddington photographed the stars in the region around the Sun during a solar eclipse. According to the theory of general relativity, stars whose light rays pass near the Sun should appear to be slightly shifted as a result of the Sun's gravitation. Eddington's observations, published the next year, confirmed Einstein's theory and were hailed at the time as a conclusive proof of general relativity. The bending of light by gravitational fields has since also been observed for distant galaxies. The most recent evidence for the theory of relativity comes from 2016, when gravitational waves, which were predicted by the theory of general relativity, were observed. These gravitational waves were produced by the merger of two black holes. Implications of special relativity for space travel. Mass dilation means that it is effectively impossible to accelerate an object with mass to the speed of light. As the closer you get to the speed of light, the more of the energy that you put into accelerating the object actually goes into increasing the mass of the object. The time taken to travel to nearby stars would therefore be significant. However, time dilation would mean that less time would pass for the passengers on the spaceship than for observers on the Earth. However, the distances would be less due to length contraction and would decrease with increasing velocity. Summary. Thought experiments. Most of Einstein's theories are based on thought experiments. Although the logic underlying these thought experiments is rigorous, they depart from reality in significant ways. When Einstein proposed his special theory of relativity in 1905, the experimental and technological capability to verify the predictions did not exist. The only experimental evidence came from the Michelson-Morley experiment. The theory of special relativity made a number of testable predictions, which have since been shown to be accurate in terms of mass dilation, time dilation, and some indirect evidence for length contraction. Einstein's general theory of relativity has been confirmed by events such as gravitational lensing, the bending of light due to the gravitational field of a mass, and, more recently, gravitational waves. There is abundant evidence for the equivalent of mass and energy. Mass dilation means that it is effectively impossible to accelerate an object with mass to the speed of light. The time taken to travel to nearby stars would therefore be significant. However, time dilation would mean that less time would pass for passengers on the spaceship than for observers on Earth. The distances would also be less due to length contraction.